welcome everyone. Today we are gathered here for Sankha Subhra Chakraborty's talk of B3. He'll be speaking on introduction to homological algebra and derived functors. His interests are in algebraic geometry. Over to you.
Thank you. Okay. Today I will be talking about very beginner-friendly introduction to homological algebra. Let me say like one or two lines on why people care about this subject. Homological algebra finds interests applications in three big fields, namely algebraic topology, algebraic geometry, and algebra. What I mean by that is, I'll talk about it in a few seconds. But of course, the historical motivation comes from algebraic topology, where we consider chain complexes based on some topological space and then perform algebraic operations on them to obtain information, the homology groups. And if your space itself has extra structures, then you can define new homologic theories on them. And if your spaces are nice enough, then you can show that there are nice isomorphisms which tell you that no matter which homology theory you consider or cohomology theory for that matter, you get the same result. So that is the algebraic topology part. Secondly, we have algebraic geometry, which I guess it's in a similar way. The application is in a similar way to algebraic topology, where again, in a sense, you are trying to mimic the methods that you had in algebraic topology, where you have your space and you have some extra structure on your space. So you define some cohomology theories on your space to prove strong results. And finally, by algebra, I just mean at least one of the instances is module theory in particular. Modules have very complicated internal structure, and homological algebra gives us nice tools to study this structure. I think that should serve as enough motivation, and now let us begin. Okay, so first of all, some notation. Over this talk, I will be repeatedly saying R module. By this, I mean a left R module where R is some unital ring. It does not matter which unital ring, and by unital I just mean the ring has one. Just pick your favorite ring with one, but the point is that it is going to stay consistent throughout the talk. And almost all of the modules I will talk about will be left modules, so I will not make that distinction separately. I will just say module, R module, something along those lines. And when I say module homomorphism, I just mean R union. And I think most of you already know what a module is. At the very least, all of you know what a vector space is. A module is simply a vector space where you replace the scalar multiplication by field elements by ring elements, essentially. What this does is, while it allows us to work in more generality, it uses the nice structure that we have when we're working with vector spaces. It's like one of the first big theorems we all learn in linear algebra, on our first courses in linear algebra, that every vector space has a basis. And the point of that is you can write every vector space as a direct sum of the copies of the base field. But this is not true in case of modules, so the structure is not as nice as vector spaces. So like you have torsion and stuff. Anyway, fine. We'll start by talking about some universal properties. Now, all of you might not know what universal properties are. In a vague sense, I start with some collection of information, and I have a bunch of objects which behave well with respect to their information. And then among the class of all such objects, some of them are the nicest in some sense, perhaps the maximal or the minimal with respect to that property. And these are the universal ones, essentially. Let me formalize this with two simple examples. So let f A to B be a module homomorphism. Then we have the kernel of f, which is simply the set of elements in A such that fx is 0. We have the image of f, which is simply f(a), and then we have quotients. The image is a submodule of the codomain, so we can form the quotient B modulo image f, and this is something called the co-kernel of f. Now we are interested in abstracting out these set theoretic constructions via universal properties. So let us look at the first one, the universal property of kernel. So my claim is that this set, along with the inclusion homomorphism, you just send each x to itself, along with the inclusion homomorphism, it satisfies the following universal property, that I have my map f from A to B, this map I for convenience. Now my claim is that given any other module homomorphism such that fg is 0, when I have something like this, then I will say that g kills f from behind. It is easier to understand what I mean. And similarly, if I have something h here such that hf is 0, then I will say h kills f from the front. But it's easier to understand what I mean rather than writing down an equation like that. Anyway, the point is if I have a g such that fg is equal to 0, then there is a unique map here which will make this diagram commute. I will give these as exercises, I suppose. For the left, comma I satisfies the universal property of kernel. And similarly for the co-kernel, I have defined it as B modulo image F. So I have a surjection B modulo image F. And my claim is that this satisfies a similar universal property, that if I have some other map H such that HF is equal to such that HF is equal to 0, then this will factor, I should call it something, X1. Then this will factor uniquely to this quotient. And this should be clear to those of you who have studied the quotient. It is, I guess, it is the same, the universal property of quotient and universal property of co-kernel. What do you study as the universal property of the quotient of, say, if I have, I guess I should write some other stuff, but if I have CD where C is a submodulo of D, C and D modules where C is a submodulo of D, then I can form the quotient D modulo C. However, this can also be interpreted as the co-kernel of this inclusion map, because the image is precisely C itself. Kernel Fi satisfies universal property of kernel, and secondly, B modulo image F, I call this phi, satisfies universal property of co-kernel. Now that we have these two, I will talk about two related universal properties which should not be difficult to verify if you have understood what is going on here. So my claim is that exercise is considered as a continuation of the exercises. Image F with the obvious map satisfies universal property of kernel of co-kernel F. What do I mean by this? I'll just draw the diagram and then it will be clear. So I have F, get B, I have the co-kernel of F, which is the modulo image of F along with this projection map. And then the kernel of this map is just going to be an injection here, such that this kills off phi in the least sense, if that is meaningful. So it is clear that the obvious choice should be image F. So I guess I have shown the exercise here myself, but anyway, the point is that image F along with this map into B satisfies the universal property of co-kernel, and similarly co-image F, which I define as A modulo kernel F along with the obvious map, which is just the projection phi prime A modulo kernel F, satisfies the universal property of co-kernel of kernel F. Now these two exercises are not particularly relevant for the purpose of our talk, but it is nice to build the intuition about universal properties, I suppose. Okay. Also, once you show these two, you should have seen the first isomorphism theorem by now in some course at least, but A modulo kernel F isomorphic to image F. So this tells you that image and co-image are canonically isomorphic. I will not elaborate on that now. What do I mean by canonical? I will explain it later on when it is indeed relevant. Okay. Now to actually useful facts about kernel and co-kernel. The point of defining these universal properties is that it lets me abstract out certain theoretic concepts. What I mean by that is one, if modulomorphism. Whenever I draw a map like this, it means modular homomorphism. Is injective. Injective means security injective. If and only if kernel f is 0. Now, this is trivial from the security version. So, I will phrase it in a slightly different manner. So, I will say 0 along with the. So, I am writing it in this notation essentially. So, I am writing it as a pair satisfying a universal property. So, 0, comma, the unit map from the 0 module to A is a kernel of F. And similarly, this is surjective if and only if 0, comma, B to 0 is a co-kernel of F. By a co-kernel and a kernel, I just mean that this pair satisfies the universal property of kernel of F, this pair satisfies the universal property of co-kernel of F. Now I will start talking about exact sequences. So suppose I have two module homomorphisms A, B, C such that GF equal to 0. Right, I guess this should be clear what I mean by this. This is just F composed G. I am omitting the composition notation for convenience. So that GF is equal to 0. Then this is the same thing as image of G. Image of F is contained in the kernel of G. Now both of these are submodules of B, and hence we can take the quotient of kernel G modulo image F. That is the homology at B in some sense. This is a definition we will come back to later on. There is no need to talk about this right now. The point is definition. If image F equal to kernel G, we say A, B, C is exact at B. I guess I should have the maps here, but basically I am referring to the same diagram. And by some abuse of notation, if I have a longer finite sequence, say something like this, if I say that this thing is exact, all I mean is that it is exact at B, exact at C, exact at B. That is all. Now let me write down some trivial stuff, trivial verifications. 0 to A to B is exact if and only if F is injective. This follows because what is the image of the 0 map? It is just the 0 element and the kernel of F. It has to be equal to 0 by our definition of exactness, so this is injective. Similarly for surjective. Now these are something slightly less trivial but of a lot of importance. 0, A, B, C, 0, F, G, F, right. Exact if and only if injective, G surjective, image F equal to kernel G. Now what I am going to do is I will replace each of these using some sort of universal property. So F injective, that will follow from whatever I did over there, I think. F is injective, we know that is a kernel of F. So that is the same thing as saying that 0 to A. By the way, when I say that something satisfies the universal property, I mean the pair, the map along with the object. Even if I write just the object or just the map, know that implicitly I mean that the pair. So for instance, like here I'm writing just the map itself, but it should be clear what I mean. Is a kernel of F. this is the same thing as C to 0 is a co-kernel of G, and this can be replaced by one of two equivalent conditions. Equivalent, assuming you have 1 and 2. A to B is a kernel of G, or G is a co-kernel of F. Now, why are these things useful when we have such nice security characterizations already? The point is that a bit later I will be trying to put structures like kernel and co-kernel, but then our objects will not be modules. So it is helpful later on. Okay. Now we come to our first result. So, I think for convenience, I will state the result on one of the higher boards because I would like to have it on the board, and I will prove it on one of these boards. So suppose I have the following commutative diagram. I'll explain what I mean in a second what I mean by commutative diagram. Is commutative diagram with exact rows. By commutative diagram, what I mean by the commutative, ignore these dotted arrows for a second, I'll talk about them in one moment. What I mean by commutativity is that you pick 2 points in your diagram, and all the paths that you can take from one point to the other, they must give you the same thing. So for instance, if my 2 points are A and E, then B composed A to B and D to E composed alpha should give you the same thing. And this holds for all of them. And in simple ladder diagrams like these, you can just check that if each of the adjacent squares commute, this will automatically give you that the entire diagram commutes, which is nice. That is what I mean by commutative diagram. Exact rows just means that, again, forget this for a second. If ABC 0 is exact and 0 DEF is exact, then there exists an map delta such that the following is exact. So kernel alpha, kernel beta, kernel gamma. This is the map delta. It is often called the connecting homomorphism. Kernel alpha, kernel beta, kernel gamma. Okay, what I mean by the dotted arrows is, even if you do not have them, this will induce an exact sequence from here to here. And if you have exactness at A, then you will have exactness at kernel of F. If you have exactness at F, then you will have exactness at co-kernel of gamma. That is all the dotted arrows mean. Now we will prove this, or well, I will try to provide a sketch of the proof and leave the rest of it as verifications. So proof sketch.
Sankha, this statement of these things
That is.
I think right on the right side.
Yeah, that was right. So let me just draw the same diagram, but we're making space for these objects as well. So A, B, C, D, E, F, kernel alpha, kernel beta, kernel gamma, and then here we have, instead of writing the abstract co-kernel, I will just work with the security realization, B modulo image alpha, B modulo image beta, and F modulo image gamma. Now let me draw the arrows. These are just inclusions. These are projections of the quotients. So alpha, beta, this is gamma. So it's the first exact sequence, the second exact sequence. And now I first want induced maps here. Now to get an induced map from the kernel of alpha to kernel of beta, you just have to show that it kernel of alpha maps inside the kernel of beta under this map, but that should follow from the commutativity of this square. Similarly, you can get an induced map here. Again, to get an induced map of the quotients, I want to show that the image of alpha contained will be lands inside E when I go under this map, but that will again follow from the commutativity of this square. So I will get induced maps here and here. So what I want is a map from here to here. So let us start with X in the kernel of gamma. This is simply the set theoretic inclusion, so X is also in C, but X is in the kernel of gamma, so gamma X is equal to 0. Also, this is exact. B C to 0 is exact at C. This means that B to C is surjective. So I can pick a pre-image for X under B to C. I will call it Y. B to C Y is equal to X. And then now let us look at commutativity of this square. Y will map to beta Y under the vertical map. And now beta Y by commutativity must map to 0 under E to F. However, this is also exact, so we have exactness at E. So the kernel of E to F must be the same thing as the image of B to E. So beta Y has an inverse image under this map. However, we also have exactness at D, which tells us that this inverse image is unique since B to E is injective. So there is a unique inverse image beta Y tilde, suppose, here, and this is where I want to end up. So I will just go modulo. So you can see what we have done. We go from here to here, then like this, like this, like this, like this. I'm not using the arrows there, but anyway, the point is, so far this is a priori. This is not even a well-defined set theoretic map because I am making a choice of pre-image. However, I will leave it to you to check that essentially because we are going modulo image alpha at the end, that will resolve any sort of well-defined issue. Check is well defined, and once you have well definedness, the next two checks should be easier. Check that this is RDM. So well definedness only shows well definedness as a set theoretic map. We still want to be a model homomorphism, except otherwise exactness is meaningless. So that is also something that is we check. And finally, check exactness. So this really gives us whatever we have from the delta. The part involving the dotted arrows does not really have anything to do with the connecting map. You can see that that should not be difficult to show. Anyway, that is a sketch of the proof of the snake level. Now we will start talking about chain complexes. Those of you who have seen some algebraic topology will be familiar with chain complexes. This is just an abstraction of that construction. So chain complex is a collection of modules indexed by the integers with maps n going from n to n minus 1. These are known as the differentials. Such that the compositions at each n are 0. Such that dn plus 1 equal to 0 for all n. So this is my definition of a chain complex. Okay, I guess now would be a good place to talk about whatever category theory ideas you should be familiar with. So I guess I'll just do that here. I won't go into the definitions of what is a category and all that because that will end up taking too much time. But think of, let me just speak vaguely for a few moments and then I'll talk about, I'll give some examples which will make the ideas clear. So category, I just mean a collection of objects with maps between them so you have maps, whatever. And there is a composition operation. So whenever you have two maps which are like this, then you should be able to compose them to get a third map in this way. So and the only real, there are really two main axioms. Like the structure of a category is very light in some sense because we want to capture as many objects as many classes of objects as we can. So the only two real axioms is that for every object there should be an identity morphism. Identity morphism just means that if you compose this with the identity morphism, you get the same thing, and similarly for composing from the back as well. And secondly, composition is associated. So this is what a category is. Examples, groups, sets, topological spaces. In the category of groups, your objects are groups and your morphisms are group homomorphisms. In sets, it is the obvious choice. You have the objects are sets and then your maps are security functions. In topological spaces, your objects are topological spaces, and in top, I suppose, that is the conventional name for the category of topological spaces. Your objects are topological spaces and your morphisms are continuous maps, and so on. You can keep going. Whenever you have some new object, there is a meaningful way to define maps between two objects of similar type. Then you can put, more often than not, you can put a category structure on this collection of objects. This is what I mean by category. And now, again, in the philosophy of this definition, I just said whenever we have objects, we would like to define maps between those objects. So now we will go meta and treat categories as objects. So what should be the maps between categories? That is the next meaningful question to ask. So if I have two categories C and D, by a map between them is simply an assignment of objects for each A in C gets mapped to some object in FA in D, and each map gets mapped to some map between the corresponding objects. Now we call such a map of categories a functor if it satisfies two properties which preserve the structure, categorical structure. Firstly, identity goes to identity, and secondly, it preserves compositions essentially. So f of f compose G is f of f compose f of G. So now, one of the simplest examples of a functor is go from the, I guess I should say non-trivial functor because I can just take the identity map sending every object to itself and every morphism to itself, and that is trivially a functor. But anyway, a simple example of a non-trivial functor is that from the category of groups, the category of sets, which is the forgetful functor. So you take a group G and you just forget the group theoretic structure and consider it as a set, as the name suggests. And this is like it should be obvious to check whether it is a functor because the structure on the category of groups itself is sort of derived from the category of sets in some sense. But anyway, I think this example suffices to explain what a functor is. Now that I have my chain complexes, I want to put a category structure on these chain complexes. So if I view these as A dots as objects, I want maps between them. So the natural definition that we will make next is that of morphisms between chain complexes. Before we do that, I'll make a comment about this thing here. Since we have these compositions as 0, we get image of Bn image of Bn plus 1 is contained in the kernel of Bn for all n. Hence, because again, this is the comment that I made earlier about the GF is 0, image f is contained in kernel G, what are submodules? The same thing holds here. This is a submodule of n, this is a submodule of n, and this is clearly a submodule of kernel of Bn. So, and I guess some notation as well I'll introduce. This notation has roots in algebraic topology. So Zn of A. Sometimes I will just write Zn of A instead, omitting the dot because it will be clear that I am referring to a chain complex. This is the kernel of del n, dn, and Bn of A dot as the image of Bn plus 1. So from this composition rule, we have that Bna is contained in Zna, and hence we can form the quotient of Zna over Bn, and that is what we are going to define as the nth homology. Yes, it's a good thing I made that comment on functors because that allows me to make the following remark. So note that if you just look at this quotient as an object and like forgive all the universal property abstraction for a second, then given a chain complex of modules, at each n, hn of A returns a module. Right, to make sense of this, I should define the category structure on chain complexes first. I'll come back to whatever I was trying to say in a few minutes. So now that I have my objects of chain complexes, I want morphisms between them. So definition, chain map. So if I have two chain complexes A dot B dot, a chain map is a collection of maps from An to Bn, again indexed by integers, such that the following diagram commutes. It is the obvious diagram that one can draw. So that this entire algebra diagram commutes out equivalently each of these squares commute. So fn minus 1 dn is the same thing as dn fn for all n. And I know I said dn twice, but it should be clear from context what I mean. Otherwise, every time I have to say dn a, dn b, and so on. A little while later, I will stop saying even the subscript n and just say d. Again, the image should make it clear what I mean. And sometimes this commutes. I should write it. Okay, and I claim that this gives me a category structure on the category of chain complexes, on the collection of chain complexes, and I will denote this category by CH dot R mod. What I mean by this is that we have that the objects of our chain complexes come from R mod, which themselves form a category, which should be clear from again. It's the same thing as we had in the case of groups. The verification that groups form a category in a sense follows from sets forming a category, because the maps are at the end of the day just set theoretic maps. The same thing can be said about modules. So R mod is the category of all left R modules over the all left modules over the ring R, and your maps are left R linear maps. So this is category of chain complexes over R mod. Yes, now whatever I was trying to talk about earlier, H and N. So my inputs are chain complexes and my outputs are modules. So this gives me the next claim, which I will leave. I'll talk about a little bit. I will not verify it is a functor. H n bar from ch dot a to from R mod to R mod is a functor for all n in Z. So already we have seen that it sends each chain complex to some module, which is this thing. But I also claim that for functoriality, the basic structure is that it must also send maps to maps. So let us look at that now. Suppose f from a dot to b dot is a chain map. What I want is a map from ZNA modulo BNA to ZNB modulo BNB. Okay, B is confusing. I should change this. So to get a reduced map like this, the obvious map that we look at is AN to BN, which is FN, and then you draw two squares here. This is FN minus 1, this is FN plus 1. The bottom square will tell you that the kernel of one maps into the kernel of the other under Fn, which will allow you to co-restrict Fn to restrict to ZNA and then co-restrict to ZNC. And then to get this, we need to show that this image maps inside this image, which will follow from the commutativity of this top square here. So you can get a natural reduced map like this, and the actual map, turns out it is simply just Z ends up being sent to F and Z. So, and like with this structure, I think that H and dot is a functor. It is not a difficult verification, and we need to check if you so wish. What shall we talk about next?
This is additive.
Right, Hn is also an additive functor. I guess I might as well talk about what is an additive functor at this point. Okay, so R mod, it has some extra structure outside of being just a category. What do I mean by that? Suppose I have two morphisms, two R linear maps from A to B. Then I can add them pointwise to get another R linear map from A to B. And what this tells me is that I can put an R module structure on the collection of all R linear maps, which I will denote home R AB as the structure of an R module by pointwise addition and scalar multiplication. Here I would make this comment that this is something that you will see over and over when you want to put some sort of structure on the collection of all maps between two objects. The common strategy is to look at the target object, and whatever dimensional structure you have on the target object, use that to induce a structure on your collection of maps. And that is the same thing that is being done here. The pointwise addition is basically relying on the addition and scalar multiplication structure on B. So this has the structure of an R module. In particular, it has the structure of an abelian group. Why is that meaningful? Another comment about functors. When I have a functor from a category C to a category D, then for each map between, and I fix two objects A, B in C, say, then for each map F from A to B, this gets mapped to some FF from FA to FB. What this tells me is that I get a map from the collection of all homomorphisms from A to B in the category C to home D FA FB. So this is the natural map that we get. Now, if both my categories are categories of modules, then in both those categories, the Hom sets will have the structure of modules over those particular rings, but we want to compare, so we will consider simply the abelian group structure for it of the extra module structure for the moment. So what I'm saying is, if my category C is equal to R mod and B is equal to say S mod, and S is some other commutative ring, some other unital ring, then F from R mod to S mod is additive. I guess you can take this as a definition. If okay, I guess this will not exactly capture whatever I'm doing over there, but I'll relate this to that in a second. But I use this to understand the definition of additive functors. This is additive if home AB, if the induced maps respect whatever extra structure we have going on, essentially. F A F B F A comma B. So this is the induced map I talked about over here, and each of these has a structure of an abelian group in whatever sense I described a few moments ago. So we say that this is additive if this is homomorphism. For all in. So basically, a functor which preserves the extra structure we have in our category, we will call it additive if it preserves that extra structure. Now, what does this have to do with Hn? Look at the category of chain complexes once. If I have two chain maps, suppose I have in A dot B dot and Fg, then I can get a chain map F plus G by simply adding coordinate wise Fn plus Gn. And then it is easy to check that this also defines a chain map. So I now have an abelian category structure, abelian group structure on the Hom sets in the category of chain complexes. And I say that, and that is enough to make this definition. So that is the same thing. We will call a map from the category of chain complexes to some other category in which the Hom sets are abelian groups additive if it has this property that if the induced maps are all abelian group homomorphisms. And as Amit pointed out, this this is in fact an additive form.
When R is not commutative,
Yeah.
you only have home to be abelian.
Right.
R modules.
I mean, I have already forgotten the R module structure because here I will have an R. If I remember the module structure, on the left hand side I have an R module structure, on the right hand side I have an S module structure. So it does not really make sense to talk about linear maps anymore. So anyway, we can only compare them as abelian groups. It's an additive functor. This you can check quite easily. In fact, like maybe I should not be writing here, but F plus G. So let me write. Fine, I'll write it somewhere else. I'll write it over there. So let's say Hn of F plus G, we want to show that this is h and f plus h and g. So let us apply to some x, I guess equivalence plus x. This is just going to be fn plus gn applied to x, the equivalence class of this thing. However, by our module structure, it is the same thing as fnx plus class of gnx, and this is the same thing as h and f x plus h and g x, and this is h and f plus h and g applied to the equivalence class of x, and this holds for all x in the homology group. So the equality holds. H and f plus g is h and f plus h and g. So this is the proof that homology is a negative function. Kernel homology. Okay. Now that we have that, now we want to talk about kernel and co-kernel of a chain map. So suppose we have f from a dot to b dot, and if I was to ask you to construct a kernel for this, the obvious choice would be to just take the chain complex. Okay, so note that even if you want to work in the set theory analog, then the kernel of a module homomorphism is a submodule of the source. But here we do not really bother with making a separate definition for sub-chain complex and so on. I claim that universal properties are enough to make sense of this. So let us try to guess what a kernel of this might be. So I will guess it to be k dot. What is k dot? Kn is equal to kernel fn. This is the set theory kernel. Right. I'm not sure I was putting in brackets. And the map from kn to an as simply the inclusion of the n kernel inside an. So this gives me a chain map here. This is what I mean by this. And my claim is that k dot with this chain map is a kernel of f in the sense of universal properties. What do I mean by this? Is there is some other map. If there is some other map, chain map G, such that if G is equal to 0, then it must factor uniquely through the kernel. And this is an easy verification because each of these kernel fn to an satisfies the universal property at the level of modules. So it is easy to check that. Oh right, I guess I should mention what I mean by fg equal to 0. Fg equals to 0 just means fgn, which is the same thing as fngn, is equal to 0 for all n in Z. And from there you can see how it follows. If I have fngn is equal to 0, then gn is going to factor uniquely to kernel fn, and this holds trivially. And similarly, let me define the co-kernel. So let me denote that by q. So qn is just bn modulo h fn, and the map that I will take from bn to qn is just the obvious choice. Right, and then this satisfies the universal property of the co-kernel in the sense that if I have some other, okay, call this G, so let me call this H. If I have some other map H, chain map H, such that HF is equal to 0, then H factors uniquely through the co-kernel. And my justification for why you should take these as meaningful definitions is that if you were to define your kernel in the obvious way, you can check that it is equivalent to defining it as something satisfying the universal property. Because right now, the thing I will do next, let me do the next thing, and then that will be a better argument for why it is useful to abstract in terms of universal properties. So, I mean, it's an easy verification, but now we want to talk about what is an injective chain complex, injective chain map, surjective chain map. Now, an obvious choice for an injective chain map would be one for which all the fn's are injective, which is all well and good and it would serve all of our purposes, but I will define it if u to be as, let me just check what I've written. Right, fn injective for all n is the same thing as, sorry, these are chain complexes and this is a chain map. Fn is injective for all n, if and only if the zero map is a kernel of f, and similarly this fn surjective for all n if and only if p to 0 is a co-kernel of f. The point of doing all this is that I want to talk about exact sequences of chain complexes. So I can abstract out the meaning of injective, surjective, exactness using universal properties. Right. So I will define what I mean by exactness of a short exact sequence of chain complexes, and I feel most of you should agree after whatever I've been talking about. Let's see. Okay, so suppose we have this diagram 0, A dot, B dot, C dot, 0. These are chain complexes and these are chain maps such that GF is equal to 0. And I should have made a comment. Whenever I direct a map from 0 to A or B to 0, I am not talking about it separately because there is only one modular. Forget that. There is just one abelian group homomorphism from the from trivial group to any abelian group. You just map the identity to identity. Similarly for backwards. Well, not similarly, but essentially everything has to go to the 0 element. So whenever I say these things, I will just talk about them without specifying what the map is because it is uniquely defined. So that is what the terminal maps are. And again, that also shows that f compose 0 is trivially 0, 0 compose G is trivially 0, so we will not have to talk about that. This way, GF equal to 0. Again, to repeat, GF equal to 0 just means it is 0 at each component for all n in Z. Now I will say that this is exact, or well, short exact sequence of chain complexes if, recall the three conditions that were written earlier. F is injective. Earlier they seemed trivial, but now, instead of being vague about what is an injective chain map, I will just work with this indirectly. So I wanted this to be injective, so I will just say F has trivial kernel. By the way, I just mean this thing. This is just one way of saying that 0 to A is a kernel of it. Sorry. Similarly, G has trivial co-kernel. And now, recall for the third condition, we have image F equals to kernel of G. And we can make that definition here that we can say it is exact if it is exact at each step. And that works, that is completely fine, but it will be equivalent to whatever I am going to write down. You can check that if you wish. That at least, even at the level of chain complexes, you can still work with concrete definitions. You do not need these universal properties. They record the security definitions precisely. I saw. F is a kernel of G, or G is a co-kernel of. Now that we have what I mean by exactness of a chain complex, well, a short exact sequence of chain complexes, we will come to the second result of this talk. Again, I will state this on a higher board so we can have it at our disposal. homology. Now, suppose I have a short exact sequence of chain complexes. G. There is an induced map. There is an induced long exact sequence. There is a long exact sequence, as the name suggests, in the homologies. What does this look like? H and V dot, H and C dot, H and V dot. Now these maps are not special. These maps follow from the functoriality of Hn. Now this is the non-trivial part. Hn minus 1k, Hn plus 1c. I'm writing the same delta, but obviously the delta will depend on these indices. And it goes on, there is Hn plus 1b, and so on. So essentially what this is telling us that if this is a short exact sequence of chain complexes, then you apply your functor to get these two maps, and then you can patch up all of these homologies in a nice manner. So we'll just try to prove this. It is basically going to be repeated application of the snake level. I should have kept that on the board for let us look at a commutative diagram. Okay, I will make a small change again because I have B dot Bn. There will be some ambiguity as to what Bn is. Does it denote the nth boundary or does it denote the nth element of the chain complex B dot? So I will just replace it with term by B dot for convenience. So 0, A dot, B dot, C dot. And I will stop writing some of the maps if it is clear from context what they should be. So again, we have the same notation as previously. Zn of A dot, or just A, is going to denote the kernel submodel of An. So this is just the kernel of An to An minus 1, and Bn of A is just the image of An plus 1 to An. I'll just write B for convenience. It should be Dn of A, Bn plus 1 of A, but I think it is clear already. Now, yes, consider this diagram. An modulo Bn A, Bn modulo Bn B, Cn modulo Bn C, and then on below which I have Cn minus 1 A, Cn minus 1 B, Cn minus 1 C, and here 0 over here, 0 over here. So my claim is that eventually we will apply snake lemma to this diagram and then show that that completes the proof. But before we get there, let us make sense of this diagram and show that it satisfies the hypothesis of snake lemma. So let me talk about this vertical map first. So what we have? We have An mapping to N minus 1 by B. Now Zn minus 1 is contained here. Zn minus 1 is the kernel of B. Why can be co-restricted? Suppose N minus 2, Bn minus 1. I guess I should write this for a second. But Zn minus 1 is just kernel of Bn minus 1. So look at anything that maps to this. This is Bnx. Now dnx is by definition in the kernel of dn minus 1, so it is in z n minus 1 a. What this means that I can co-restrict this map. The image of dn is contained in the kernel of dn minus 1 by definition, so I can just co-restrict it to get z n minus 1 a. This is just sectorial inclusion. This is just dn tilde, I suppose. Now again, now you need to fix the domain. But to get a map out of the quotient, we just have to show that the thing in the denominator goes to 0, and that is trivial. If you take something in DNA, it is the image of something from n plus 1, say y. So say x in BLA comes from y, but then y under this composition is 0, so it must be 0 under this composition as well, because this is injective. So that shows that this factors to the quotient. This is the projection map. This is the factorization. And I mean, one can guess what this map is. This is simply the equivalence class of A gets sent to the equivalence class. Sorry, not even equivalence class. We have really factors. Just gets sent to B and Z. I guess I did not write Z because we were not working with the homological. Anyway, the point is now we have made sense of these vertical maps. The horizontal maps are the obvious maps. They are reduced from 5. I'll talk about them in one go, I guess. I'll talk about how we get them and also why they are exact, which is one of the conditions for snake limit. So consider, let us do the top one first. Consider this diagram: n plus 1, an, sorry, an minus 1, and then what do we have? Just a second. n plus 1, n plus 1, cn plus 1, and then n, bn, cn. You can check that exactness of that thing means the same thing as each of the chain complexes 0, n, bn, cn is exact, 0, n, bn, cn, 0 is exact, and the ladder diagram, the big ladder diagram for groups. So that is what I shall use here. 0, this, 0. This row is exact. This row is exact. These are the differentials. Now look at what we have here. It is exactly this. So this is going to give me a chain complex. But one more thing. What are the kernels and co-kernels here? This is just z n plus 1a. This is z n plus 1b. This is z n plus 1c. And here we have the co-kernels. And the co-kernel is an modulo bna. bn modulo bn modulo bnb, and then cn modulo bnc. Now by the snake lemma we get an exact sequence like this. Note that this is more than what we want. We just want exactness at bn modulo bn and then cn modulo bn. So we just truncate this exact sequence over here, and this gives us the top row. And I guess I should have mentioned once why this diagram is commutative, but I think that should be obvious. You can, if you want to, just do the sectorial verifications yourself. It is not difficult. But yeah, the diagram is commutative, and we are trying to show that the rows are exact. So we have shown that the top row is exact, and then by a similar argument, you can show that the bottom row is exact. You have a minus 1, dn minus 1, cn minus 1, a minus 2, dn minus 2, cn minus 2. And then for the bottom, you will have the co-kernels. I will not bother writing them because we do not care about them. I'll just write the kernels on top. Cn minus 1 is, cn minus 1 b, d, cn minus 1 c. And then again, because each of these is exact, we will get an exact sequence like this. But note that we do not really care about this part. We just want exactness at cn minus 1, cn minus 1, cn minus 1b, and we can get that by just truncating here. So now we are in the setup of snake lemma. We have a commutative diagram of this shape with exact rows. Hence we apply snake level to get that end of exact sequence. So this time the terminal zeros will not be there. So let us look at what the kernels and co-kernels are here. So let us look at I'll write it here for clarity. So kernel of in module of DNA. Let's just write out the set. This is the collection of equivalence classes such that dx is 0. But dx is 0 means x is in ZNA. So this is nothing but ZNA modulo BNA, which is precisely the nth homology of NO. Similarly, let us look at the co-kernel of this map. So the co-kernel is Zn minus 1a modulo the image of this map. But the image of this map is the same thing as Dn minus 1a. Because what is this? This is just the co-restriction. The co-restriction of our original Dn. And the quotient map is not going to change what the image is. So the image is precisely the same thing as Dn minus 1a. So we have Zn minus 1a modulo Dn minus 1a, which is again simply the n minus 1th homology of A dot. So if I were to complete this diagram, I get HNA, HNB, HNC, HN minus 1A, HN minus 1B, HN minus 1C, and then we get a log exact sequence by snake level, which proves the result. Okay, now that we have all these tools, I will talk about what is the main problem that we are trying to solve using all these tools. And as soon as I state the problem, I'm going to start to work more machinery, but bear with me. So the main idea, okay. So earlier we talked about additive functors. Additive functors are maps, functors from categories in which the home sets are Abelian groups to functors between categories whose home sets are Abelian groups. There is a lot of detail I'm leaving out for convenience, but I'm working telling you all the least amount of information that is required to understand what I'm trying to express. Anyway, so that was an additive functor. Now, suppose both your categories C and D, your source and target categories, have sufficient structure to make sense of exact sequences. I will not elaborate on this, but so for convenience, if you wish, you may assume both of them are module categories. Exactness is defined as one, or say one is a module category and one is a category of chain complexes over some other category of modules. But basically, assume that both of them you can make sense of exact sequences and so on. Now, if C to D is right exact, if suppose in C I have a short exact sequence 0, A, B, C, 0, if for any such short exact sequence applying F preserves exactness at B, at FB and FC, then we say F is right exact. Basically, for short exact sequences, it preserves exactness on the right hand side. That is all. But yeah, what does in this thing be exact mean? Whatever is the appropriate notion of exactness in the category B. So you assume C and D has sufficient structure. Without loss of generality, assume they are module categories. This sort of justification, this I should not say without loss of generality, but up to some big theorem, some big embedded theorem, all this will make sense. Even in module, especially in module categories. Anyway, I will not start talking about that now. So this is what I mean by right exact functor. Now, take it as a fact that we want to preserve exactness. I mean, even if you do not know much about these things, it would seem like a nice property to preserve. Oh, I guess I should have made this comment. But when I apply F, I get FF, FB, and at the very least I get that this is a chain complex because f of g composed f. Right, I should might as well state this small result which I shall not prove, but you can try proving it. Yes, I think it is not difficult to prove it. Left, sure. Left slash right exact functors are additive. If you cannot prove it, like talk to me later on, I will point you to references for this. But we have this. We have additive functors. So f of g composed f. Oh, for that I don't even need additive. But anyway, the point is that f g composed f is the same thing as f of g composed f, but g composed f is 0 in the domain category, so it is just f of 0 and then fine. So to conclude that f0 is 0, I think additive functor is sufficient. But yeah, exact functors. Fine. My goal is to extend this into a long exact sequence on the left. This is my setup. And the rest of this talk is going to be devoted to solving this problem. Okay. Now we start talking about more machinery. But before I talk about that, let me just give an outline of how the rest of this talk will go. I just simply want a long exact sequence on the left. Now, as soon as I say long exact sequence, like that should be the thing you should look at. That is a method to obtain long exact sequences that I am talking about. So it is natural to expect that will be the P2. But notice that we have to start with a short exact sequence of complexes of modules, not the modules themselves. So now our goal is going to be, starting with some module, we will transfer the information of this module into a chain complex in a meaningful way. That leads us to projective resolution. What is the projective object? Be a projective module if we go with the classical definition first and then I'll state an equivalent criterion which you can try to prove later on. P is a projective module if suppose you have a surjective modular homomorphism from A to B and any modular homomorphism from P to B, then there exists a map from P to A making this diagram common. Note that even though it looks similar to the universal property diagrams that we used to draw, this is not unique. There is just some map from P to A making this diagram commune, but this holds whenever you have this structure. That is all. This is the definition of projective module. And then proposition P projective if and only if P direct sum Q is free for some Q. So what do I mean by this? That this is isomorphic to some free module. I think, okay, what is a free module? A free module is simply a module with a basis. That is all. Like in vector spaces, all your vector spaces have bases. So once you have a basis, your module decomposes as a direct sum of your indexing, cardinality of indexing set many copies of the base field. Same thing happens here. If you have a free module with a basis, say I, basis indexed by the set I, then your module decomposes as a direct sum of the cardinality of the indexing set many copies of R, where R is considered as a module over itself in a natural way. So this is just saying that P is projective if only is this is if only if it is a direct sum of a free module. The purpose of stating this equivalent definition is that it gives me the following result easily. Thirdly, free modules are projective. I would recommend trying to prove this directly as well. It is not hard. It is nice. You can see how the basis is being used. So, I guess an exercise would be to try proving free modules are projective directly without using this equivalent criterion. Anyway, what is next? Let's see. Right, I have defined projective objects. Now I will define a projective resolution. Definition. projective resolution for M is some vector module is a chain complex P dot with Pn 0 for n negative and a map epsilon from P naught to M such that T2, T1, T0, N0 is exact. So projective resolution is simply a chain complex. Wait, 1 second. Sorry. Chain complex of projective modules. Yes, otherwise it's sort of useless. A chain complex of projective modules. That just means each Pn, each non-trivial Pn is projective, and negative ones we define it to be 0, and there is a surjection from P0 to M such that this is exact. Now going forward, I will denote this as P dot epsilon M. When I say this thing, this just summarizes the definition. Okay, so I have this, and now I will leave it as an exercise to check that. Right, fine. Let me define what I want you to check first, and then I will leave it. So my claim is that the category of left arm modules has enough inject. I mean that is also true, but this is not what I want to say here. Sorry. Has enough projectives. What I mean by that is that given any arm module M, you can find a projective module P surjecting onto it. Exercise. Given M, show there exists P projective with a surjection. Not sure if I mentioned this, but like this is my notation for surjective maps. This is technically the notation for injective maps, but so far I think I've been writing this. This is better when I want to show that it is not just an injective map, but rather you have set theoretic inclusion, which is I guess set theoretically stronger. Anyway, that is irrelevant. So this should be an easy exercise from whatever I've written on that cardboard over there. But try doing this. I will use this in the next result. Provision. Every module M admits projective resolution. Okay. Good. The proof is inductive. Let us start with M here. And now I will just use this exercise over and over. So let me start with some projective module P0, surjecting onto M, follow the map epsilon. Now look at the kernel of epsilon. This as an inclusion here. And now I will apply this exercise to this kernel of epsilon to get a surjection from a projective module onto kernel of epsilon. And then I will define my first differential as this composition. And then you just repeat this inductively. You look at kernel of D1, and then you take a projective module surjecting onto the kernel of D1, and take your next differential to be this composition. And you keep going like this. So that this is a chain complex follows automatically. This is, we can put a 0 here because epsilon is injected. Because epsilon D1 is the same thing as epsilon times this composition, but this composition is 0, so epsilon D1 is 0. Similarly, D1 D2 is equal to D1 compose this, but D1 compose this is 0, so the entire composition, so D1 D2 is 0, and so on. By inductively, it is a chain complex. All that remains is to check it is an exactness, which I will just leave it as a check. It is not difficult. Check it is exact. However, I will use this. I will quickly talk about a different way to check exactness, which is also a nice idea when working with more general structures. Okay, so if I have a module homomorphism f from A to B, then I have the image. Here you can take the image as either a kernel of co-kernel of f or just the set theoretic image, but the point is that f factorizes as the composition of an injective map and a surjective map through the image of f. Now my claim is, in fact, take it as an exercise. Suppose there is some other module Z with a pair of maps such that let me call this M, let me call this E, F equal to M P equal to M prime E prime, M prime M injective, and then E prime E surjective. The exercise is to show that there exists a unique homomorphism from image F to Z, which is in fact an isomorphism, and it is an isomorphism in a natural way. What I mean by that is, image F satisfies a certain universal property. You can use that universal property to get a map from image F to Z, and by natural isomorphism I mean that that induced map is in fact an isomorphism. So it will follow from there. Note that this is the point what I am trying to make. D1 is going to factor in this fashion through the image of D1. In fact, this is also set theoretic inclusion. And then this will give me an induced map, or in whichever direction. I mean, it's an isomorphism, so I don't really care. So you can check that image D1 is equal to kernel of epsilon. And because these are set theoretic inclusions, you can get equality here, in fact, which will show you exactness at P dot. And inductively, you can get exactness at all P's. But this is also a nice way to check exactness. That completes our proof of every module has a projective resolution. Now, one immediate thing to note is that there is not a unique format. Literally, there is no unique projective resolution P given a module. You are making choices at each step. You are picking P0, you are picking P1, you are picking P2. But the point is that this is not going to affect anything that we do later on, and I will try to justify that in the time it has. Let us continue for a moment. Okay. Small comment. No. Suppose P dot to M is a projective resolution. Then check that the zeroth homology of P dot is, or well, at the very least, isomorphic. It is not equal, you can check it. It is simply the co-kernel of P1 to P0, which has to be M, because putting M at the end makes it exact. If you can accept that as a proof. Okay, right. I mentioned that because talking about projective resolutions involves making some arbitrary choices, which we do not really want to do. We want our choices to be, we want our constructions to be invariant of any arbitrary choices. So now I'm going to define a way to compare chain complexes. I mean, of course, one way to compare is the notion of comparison that we have in every category, isomorphism. Because I put a category structure, I can define two chain complexes to be isomorphic if I have two chain maps going in opposite directions, and the compositions with me identity maps. But that turns out to be too strong of a condition. We will weaken one notion. The point is, we do not want to preserve the chain complexes exactly. What we want is to preserve the homologies, which I guess, okay, fine. The precise way to preserve homologies is by weakening to something called quasi-isomorphism, but I'm not going to bother defining that. I will just define a different way to weaken comparison. Chain homotopy. So I'm not sure if it is motivated by homotopy of topological spaces, but at least those of you who know the basic concepts of homotopy, the basic definitions, you will see the parallels coming up. Okay, motivation. Suppose I have two chain complexes A dot B dot, and I have, this is not a chain map, it's a degree 1 map. Degree 1. What I mean by this? It is simply a collection of module homomorphisms from N to Bn plus 1. This is all. By a degree 1 map, I just mean a collection of module homomorphisms from N to Bn plus 1. Note that this is different from chain map in the sense that I am not requiring this to commute with the differentials. It need not. The point of doing this is, if we draw this diagram, N minus 1, sorry, N plus 1, Bn plus 1, Bn, Bn minus 1, this is Sn minus 1, this is Sn, and I should write some of the differentials, Bn, Bn plus 1, Bn, Bn plus 1. Now my claim is that, look at this composition and this composition. Both of them are module homomorphisms from An to Bn, so I can add them to get a module homomorphism Fn as Sn minus 1 Bn plus, what is it, Bn plus 1 Sn. Now my claim is that this Fn is a chain map, in the sense that this commutes to the differentials. So I want to show that I have Fn here, and I have Fn minus 1 here, this is Sn minus 2, this is Bn minus 1. So my claim is that, let's see, what is my claim? So this square commutes essentially. So Bn Fn, Bn Fn is equal to Fn minus 1 Bn. Now for convenience, I will start omitting the subscripts for the differentials. So let us compute the left hand side, dfn. This is equal to d of, what is fn? Sn minus 1 bn plus bn plus 1 Sn. Note that after it goes inside, decomposed dn plus 1 is going to be 0, so this term is going to die off, and the only thing that will survive is d Sn minus 1 dn. And similarly, let us compute the right hand side now, fn minus 1 b. Fn minus 1, what is Fn minus 1? Fn minus 1 is this thing, so Sn minus 2 dn minus 1, Sn minus 2 dn minus 1 plus, what is the other thing? dn Sn minus 1. dn Sn minus 1, and then multiply by d on the right. So again, dn minus 1 composed b is going to 0, so this term is going to die off. So all we are left with is bn Sn minus 1 b. And if you were to check the subscripts, you would see that these two are one and the same. So this proves that Fn is a chain map. The takeaway is that now that we have a chain map, let us look at H and F. Hn is a functor, recall. So I have H and F a map from Hn A dot to Hn B dot. So let me take some element here. In the class corresponding to element Z. This gets mapped to right. This gets mapped to modulo S D plus D S. Again, this is abuse of notation. I am letting go of the subscripts. Just there, put the appropriate subscripts such that this makes sense. Z. And now my claim is that this is 0, and that is not difficult. Let me just show it quickly. So SB, so we can expand it out to get SBZ plus BSZ. Now this term is 0 because Z comes from the kernel of del N, Dn. Because Z, what is this thing? This is Zn modulo Bn. So Z comes from Zn, and hence Bz is 0. So that shows this term is 0. And now let us look at DSZ. Dx, even on the right hand side we have, sorry about this. We have Zn modulo Bn. So we are going modulo the image of the differential, but this is precisely in the image of the differential. So this is 0. Okay. The takeaway from all of this is that when I have a degree 1 map and I consider the chain map SD plus DS, it induces the zero map in homology. That is all. This is going to motivate the next few definitions. We say f from A to B is null homotopy if f equals to sd plus ds for some degree 1 map s. Okay, this looks like maps, but that's what. Definition: suppose we have a parallel pair of chain maps. If G are said to be chain homotopy, if f minus G is null homotopy. Now this should, at least those of you who have seen it, for those of you who have seen it, this should remind you of topology from homotopy from topology, where first you define two homotopy of continuous maps, and then once you have this, you use this to put an equivalence on the spaces themselves, where you say that two spaces are homotopy equivalent if instead of maps which compose to the identity, you have maps which whose compositions are homotopy to the identity map, and that is what we will do as well. We will use it to compare chain complexes. Definition. Equivalence if there exists G dot A dot such that what do we have? Fg is chain homotopy to the identity of B, I'll denote it by 1 B dot, and then Gf is chain homotopy to identity of B dot. And this you have to check that the identity maps are chain maps. For each n, you just map it to n by the identity on n. It's trivially a chain map. Okay. Now that we have a way to compare chain complexes, we will see why the projective resolutions are the right way to go, essentially. Now, this result I will not prove. I might as well use the ports I have, I suppose.
Yeah, sure.
Comparison here. Let P dot be projective resolution for F. Let F from N to N be R-linear. Given a resolution Q dot, this is theta of n, there exists a chain map F tilde extending F. What do I mean by extending F? We have n T1, 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 n. So the degree minus 1 component of the chain map F tilde is just F. That is all it means. F tilde 0, F tilde 1. And this extension is unique up to chain homotopy. I shall not prove this result, but I have a proof for real, but I don't think I will have time to prove it. I'll point to a reference at the end for it. And I have one more theorem, which I will state. I think sure I've used that for So even though I will prove it, I will at the very least try to motivate where this thing comes from. But this is going to be the key tool that But anyway, recall that what I want to do is I want to apply the long exact sequence to a short exact sequence of chain complexes, but I only start with a short exact sequence of modules. So this is going to be the key tool that is going to help us make that jump from modules to complexes. Suppose we have a short exact sequence 0, A, B, C, 0 of modules, S, E, S of modules, and we make projective resolutions for the two ends, P dot to A, R dot to C, projective resolutions. Let me draw the picture here. So 0, A, B, C, 0, and we have picked P0, P1, R0, R1. So those are also exact. Then there exists a projective resolution Q0 of B with, it's not just any projective resolution, we can choose one such that, okay, I am now realizing that I have been writing my coulomb as all zeros. Do not confuse this with Q0, but I should have. So hopefully it will not cause too much confusion in the previous course. But anyway, a projective resolution with, what did I want to say? Right. Qn is module isomorphic to Pn direct sum Qn. And so this helps. So you can see, a horseshoe shape in some sense, and we are completing the horseshoe by inserting the Qn's. And a short exact sequence of chain complexes zero, P dot, P dot, R dot. So what this means is we can complete these. So now we have essentially this diagram is the same thing as just saying this is 0, A, B, C, 0, and then here we have P dot, Q dot, R dot. This is a commutative diagram, and both of these columns are exact. Okay, this is the horseshoe lemma. Now we are finally ready to get sufficient machinery to answer our question. Okay, let's move to this one. What was our question? Right. Actually, it is. Derived or left? Derived. Okay, so let us do a construction first, and I will not justify it at the moment, but whatever we do immediately after this is going to justify why this is meaningful. So firstly, for each module M, choose a projective resolution P dot 12, and then define the ith left derived right. So the setup is f right exact. So f is a right exact functor. When we apply to short exact even 0 ABC 0, we get fa fb fc 0. So we want essentially on the left. That is where this notation comes from, the ith left derived functor. L-I-F of M as the ith homology of F P dot. Okay. Now, one thing to notice is that on the left hand side, I am defining it as an operation on the module M, but on the right hand side, it depends only on the chain complex P dot. So, one should be able to verify that this does not depend on our choice of projective resolution. And although I will not go into the details of that verification here, it is going to follow from the comparison theorem. One can try and show it. Because think of this, like choose two different projective resolutions for the same module and consider the identity map from that module. Now any chain map extending the identity map must be chain homotopic to, will be chain homotopic to a map for which the -1th map is the identity map. So that argument can be extended to show that this is in fact well defined. So you can try showing well defined this, it is not too bad. But that is fine. So I have this. Okay, now after this, right. Now after this, how do we complete this thing? So I have FA, FB, FC 0. I want to extend this on the left. How do I do this? That is what we will answer now. We will do this using these LIFs. So first of all, we start with 0, A, B, C, 0. Then we choose projective resolutions for A and C. We apply the horseshoe lemma over there to get Q dot, a projective resolution for B, such that this is exact and commutes. So that this row is exact and the diagram commutes. Now we will forget about our original sequence 0 ABCC and focus all of our attention on 0 PQR. Okay, now is a good time to talk about split sequences. Instead of presenting them with the generality of chain complexes, we will just talk about them for split short exact sequences. So a short exact sequence 0, A, B, C, 0 is split if it is isomorphic to 0, A direction C, C, 0. I think here you take identity A, identity C. Basically, there exists an isomorphism from B to A direction C such that this entire diagram comes. This is what we mean by split short exact sequence. Now, my claim is, again, this is also stuff that I will not prove, but it is a heuristic justification for why, when I apply F to this thing, exactness is indeed preserved everywhere, not just on the left. This is what I'm trying to justify at the moment. F r dot 0. So, my first claim is that right, F is right exact. I think I wrote down at some point that left right functors are additive. So F is additive. And my claim is that additive functors preserve split short exact sequences. This is very interesting. I will not go into why this is true at the moment, but a nice fact, well, it's not nice, but it's interesting, is that it does not, additive functors do not preserve exactness. I mean, in particular, if you have a left exact functor which is not right exact, it is additive, but it is not exact. So additive functors do not preserve exactness. But if on top of exactness you impose splitness, this combo can be turned into some, like, split exactness can be characterized as, okay, so 0 is another result, 0 A, B, C, 0 is split exact. This you can take as an exercise. If you don't believe, the identity map, by identity I just mean zeros go to the zeros, A go to A, B go to A, A goes to A, B goes to B, C goes to C, and the chain map, that chain map essentially. If the identity one from, I guess, it's okay, I think it's clear what I mean. If the identity map is null homotopy. Now, try proving this and suppose grant this result. What this tells me is that the identity map, I can write it down as an equation. SD plus DS. Once I have 1 is equal to SD plus DS, I apply my additive functor F. The point of additive functors is that they preserve my abelian loop equations, linear equations essentially. So if I apply F to this entire thing, 1 is equal to SD plus DS, then I get F of 1. Remember when I talked about functors at the beginning that identity maps go to identity maps, that was one of the axioms for functor reality. So this gives me identity is equal to Fs, and because of additivity, FSD, F of SD plus DS is the same thing as FSD plus FDS. Fs, FD plus FD, Fs. FDs are precisely the differentials in the target category. These are precisely the FDs. And Fs, this is precisely a degree 1 map with such that FSD, so if I just rename these as D primes. So what is this? Fs D prime plus D prime Fs is equal to 1. But this means that the identity map in the target category is also null homotopy. And then I will appeal to my exercise, I suppose, again. And this tells me that this is split exact. So if you are split exact, then an additive functor is going to preserve that, but it will not preserve exactness, which is very interesting. Anyway, that is all. That is my justification for why this thing is exact. Now, finally, we have a short exact sequence of chain complexes, and we will apply the long exact sequence in homology. So, for convenience, I'll just write it down here. If E dot, I'll just write it if U, if I. exact sequence in homology to get the following: hn plus 1 fq, hn plus 1 fq. I'm omitting the brackets for lack of space. Sure, that will be my excuse. hn plus 1 fr. This will be our connecting homomorphism coming from the Elias theorem. hn f p, hn f q, hn f r, and then again the connecting homomorphism will give me h n minus 1 f minus p and hn minus 1 f q and so on. However, note what these terms are. What did I define over there as the derived functor? HIFP as LIFM. So this thing can be written as L n plus 1 f of Q is the polynomial resolution corresponding to A, I think. Where did I write down my original short exact sequence? I think I realized it.
It is to be.
I should have kept it on the board. Okay, I'll try to get it something. 0 A B C 0 B dot B dot R dot 0 0. So this is just ln f1b and this is just ln f1c. So we can rewrite this as, I'll omit these terms so I have to write this, but essentially ln plus 1 f of c and then ln f a, ln f b, ln f c, and then ln minus 1 f a. So you should be able to see that we are nearly done. We are getting a decreasing sequence and we are actually done. Let us just look at what is L naught f. L naught f. So I have the zeroth homology of fp dot, let's say. So fp dot is the chain complex fp0, 0, fp1, 0, sorry, fp2. So L naught f is just H0 of fp dot. So we want to compute the homology here. Now I will leave it as an exercise. I think probably I have given it as an exercise before. But essentially the homology here is going to be the co-kernel of this map. Essentially what can I put over here to make this new thing exact? And that is precisely nothing but the co-kernel of fp1 to fp0. And because f is right exact, this is nothing but f times co-kernel of p1 to p0. I had made a comment earlier about how this is nothing but the module we are considering. So this is just Fn. So L naught f is the same, this should be L naught f of A, I suppose. The point is L naught f is the same thing as f itself. So if I continue my long exact sequence and I see where it ends, let's just look at that once. I have L1 FB, L1 FC, L0 FA, L0 FB, L0 FC. However, this is A, this is B, this is C. Sorry. FA, FB, FC, and this is just 0. So the exact sequence ends here. So we have concluded whatever the problem was that I stated of extending FA, 0 on the left, we have done it using the left derived functors. And this concludes the construction and I guess justification. Now I will give one example of a useful left derived functor. Now this example might not be approachable to the second years, they have probably not learned it in the course, but I'll say one or two lines about what it is, but it tells a product essentially. So if I have a Okay, for the sake of explanation, let us just consider modules over a commutative ring. Then I can treat them as a left module and a right module in a consistent manner, and then I can take the tensor product and get a left module and right module structure on the tensor product. So the point is, are commutative. Then, if I have two modules Mn over R, then I can take their tensor product. What is the point of this tensor product? Let me talk about the characteristic property first, and then I will talk about the basic application of the tensor product. So firstly, the point is, if you have a bilinear map, it characterizes the bilinear maps from the direct product of M and N to some other module Z as linear maps from the tensor product to the same module Z. So like you can write it as biline M cross N Z is the same thing as hom R, I suppose. I guess this should also be R bilinear. Hom R M tensor N Z. But this is the characterizing, like tensor product is defined using this universal property that bilinear maps from M cross N to Z factor uniquely through the tensor product as a linear map from tensor product to your direct module. Now the construction is not too hard. You can take the free module and then quotient by whatever relations you want. Some self-resolved, and then you can show that that quotient satisfies the universal property of tensor product. But that is not useful. It is useful to do things like if you do not know enough category theory to apply adjointness of tensor product and all that, then the construction is your only hope in certain instances. But like I will talk about this right now. But anyway, this is the characterizing property of tensor product, and the most useful application is something called base change. A base change is basically when you have an algebra over one ring. What is an algebra over a ring? So S is an R algebra. Whatever I'm saying right now, I take everything to be commutative. Why not? Commutative ambiguity is an R algebra if R2S is a module ring homomorphism. Sorry, S and R are rings, ring home. So what this does is this gives you a very natural R module structure on the ring S. In how do I define that? R dot S is simply phi R S, and you can check that this puts an R module structure on S. So using this, I can put S module structures, R module structures whenever I have a ring homomorphism like this. So the point is that suppose I have an algebra S1. An R algebra S1, then suppose I have two such R algebras S2. Then I will say I want to consider S2 as an S1 algebra. What I am going to do, I shall take the tensor product over R, and then this is going to have a natural S1 module structure. And like for all intents and purposes, this is a nice way to change the scalars. Essentially, there is this thing called extension of scalars. Hopefully, I'm not confusing it. I think restriction of scalars is the one where you go backwards. Anyway, but yeah, this is the main application of tensor product. You will all see it in your third year presumably, hopefully. Anyway, now let's just go back to our ring having only unity and not necessarily being commutative, and consider a left. Okay, now left and right is important. Left R module B. Then firstly is a functor from mod R to this is the category of right R modules over the ring R. This is the category of abelian groups. So you start with a module M here, R module, you just send it to M tensor B, and like if you have a morphism M to N, you just send it to what is it? If this is F, then F tensor 1 from M tensor B to N tensor B. This is the structure of the functor. Take it as an exercise to check that it is indeed functorial, it is not a difficult functor. In fact, also take it as an exercise to check that it is additive, but this will be a consequence of whatever I talk about next as well. Now, it is right exact. How does one show this? Now, I will speak of three approaches. I might as well write them down. Sure, this will go. First approach, this is the thing I was talking about earlier, that when you do not know too much category theory or are not too comfortable, then you always go back to your security construction. So the first approach is brute force. I'm not sure if I'm writing this down, but use construction of tensor products. And you can do it with the construction. It is not a very elegant proof, but it will get you there. So if you do not want to actually do too much higher algebra, then this is one proof. The other two proofs will both use something called the Hom tensor adjunction. What is adjointness? What is an adjunction? Suppose I have, hopefully I will not mess up the definitions or notation. Suppose I have two categories L, C and D. Let L be a functor from C to D, and let R be a functor from D to C. We say that L is left adjoint. I'm sorry, I do not recall what the notation is, what side the direction is, but L is, I just write it in words to avoid writing something wrong. L is left adjoint to R, or equivalently R is right adjoint to L if, first of all, for all objects A and B, there is a natural isomorphism from Hom LA B. So B is in L maps into D, so this is over D. So for all A in C, B in D, there is a natural isomorphism from this to Hom C A comma R B. And I mean, isomorphism is fine. What do I mean by natural? Natural means if you vary the coordinates, it still works well. So suppose there is a map from A to A prime, B to B prime. By functoriality, it is going to induce maps to Hom L A prime B, Hom A prime. This is by functoriality of L, R, and Hom itself, which I'm not bothered about it, but it should be clear what the map should be. Hom A prime R B. Again, this natural isomorphism is for all A in C, B in B. Thus, we can take A to be A prime and get a natural isomorphism here. Similarly, we can vary B. So Hom L A B prime. This will be Hom A R B prime. And again, here we take the same way, but replace our B by B prime to get natural isomorphism here. The point of say, okay, fine, I should just say isomorphisms. Naturality means all of these squares commute. This is what it means for, this is the definition of a pair of adjoint functors. This is sufficient, we do not need any more abstraction than this. This is good enough. Now, once you have this fact, you also have the following fact. You can try proving this if you know tensor product. Tensor is left adjoint to Hom. I shall not go into details of what this means. If you want, you can talk to me later. I'll tell you more about it, or point to references. I mean, if you want, you can just search Hom tensor adjunction and you'll get what it is. But the point is that, okay, the second method, right, show right exact directly using at the adjunction. Now tensoring is right. I want to show tensoring is right exact. So basically, you start with the next sequence a 0 ABC 0 0 and for any module M you want to show this A tensor M, B tensor M, C tensor M 0. You want to show that this is exact. And my point is that you can do it using the adjunction. So that is one proof. That is a doable proof. It is not too bad. Now the final proof, it appeals to so even more machinery, and like at this point, you start asking the question that is a short proof really meaningful if you don't understand all the steps that go into it. But at the very least, it is faster than both of the other methods. So I will not explain this, but I'll just say it for the sake of proving, I guess. Left adjoints, commute with colimits. Colimits are basically objects which satisfy universal properties similar to direct sum and co-kernel, in the sense that you have some sort of unique factorization and it factors out of the universal object. In a very vague sense, that is what a colimit is. So left adjoints come with colimits, in particular with finite colimits. And this is equivalent to being right exact. Why? What is happening when we do right exactness? There are two things involved essentially. So if I have A, B, C, 0, then FA, FB, FC, 0. So exactness is being presented B and C. Essentially, the fact that FB to FC is a co-kernel of FA to FB. So if I can show that my functor F preserves co-kernels, what does that mean? That a co-kernel of A to B, which is B to C by exactness, gets sent to a co-kernel of FA to FB. So that makes sense why commuting with co-kernel in particular is a finite limit, because like the number of objects in your diagram for the defining object, like co-kernel, yeah, I mean finite colimit just means there are finitely many objects involved in the definition. So co-kernel is a finite colimit, hence right exact. So, but like this proof relies on like this fact, left adjoints commute with arbitrary colimits, and like this is highly non-trivial. I will not expect any of you to do this as an exercise. But if you are willing to take it as a black box theorem along with some other similar black box theorems that categorically gives you, then it is a proof, I suppose. Anyway, the point of all of this was that tensoring is right exact, and then in the context of whatever we have talked about today, we can construct its left derived functors. So, I guess, sure. So we define store, I think the notations are in A comma B as Ln of the functor, which is and applied to A. So the left derived functors of this functor applied to the left derived functor of this tensoring functor applied to A. Now, a natural question to ask is that this expression does not tell you that this is what has been chosen as the functor. Another choice for defining it would have been this thing. Because this is also right exact by similar arguments, and hence you can construct its left derived functors and apply to the I think left R module P. So why is this not the definition? It can be shown using more technical machinery from homological algebra, like double complexes and so on, which is a special case of something called spectral sequences, which finds tremendous use in algebraic topology and algebraic geometry. At least one of the concrete ways in which I'm familiar with is basically if your topological space is nice enough, then you can break it up, apply certain functors, and then get double complexity. Anyway, the point is you can use more machinery to show that these two things give you the same thing. And this is nice, not only in the sense that this left hand side is well defined and you do not have to worry about which functor you are picking. It is also good for computation because one of your objects, A or B, might be nicer than the other. So in that case, you choose the resolution for the other object because tensoring with the nice object will preserve exactness better in general. Like whatever that means. I think okay, fine. I would start saying that but tomorrow's talk will use these ideas at some places. Anyway, this is all for Tor. This is an example of a left derived functor. I think I'm mostly done. Okay, so we have constructed the left derived functors of a right exact functor. A natural question to ask is, what do we do if my functor is left exact? So instead of preserving exactness in the BFC, it preserves it on the left hand side. 0, A, B, C, 0. Suppose it goes to 0, F, A, F, B, F, C. Suppose exactness is preserved here and here. Now I want to extend it on the right. Then we change our notion of resolutions. We replace our projective object by an injective object, which is a categorical dual. What does that mean? You just reverse all the arrows into defining in the definition of a projective module. So I injective module if suppose you have any injective homomorphism from A to B, and suppose for projective case the map was from the projective into the object, so it now here will be backwards, and you have any R module homomorphism from A to I. If there is an R module homomorphism from B to I making this commute, then you say that this is injective. You can check that this is the same thing as projective, but I have just reversed all the arrows essentially, which is what we mean when we say categorical dual, whatever that means. Okay, what that simply means is that the dual of a category is simply another category which has the same set of objects with all the arrows reversed. So you can see that the projective object in the category of modules is the same thing as injective object in the dual category. That is all I mean. What else? Right. So and then you extend all the theory that we have done today in similar ways to okay. This I should note, showing that the category of modules has injective objects has enough injectives. So for any module M, there is an injective object I such that with an injective map into it. This is non-trivial as compared to doing it for projective modules. There is a nice way to do it, but I do not think I have the time to talk about it now, so I will not bother. Anyway, right. Anyway, you can construct injective resolutions in this way. And then, since home is left exact, again, why is home left exact? You can just dualize whatever arguments are done over here. However, that is not a very good way to show home is left exact. It is much better to try to do it directly. You can do it. It is not difficult at all. That gives more some measure of insight as well into why home is left exact as compared to saying right adjoint with limits. Anyway, the point is that you can construct the right derived functors of home, and then that gives you what are called the X functors. Tomorrow's talk, Amit is going to highlight why we care about Tor and X and how you can apply them to study groups or something along those lines. I'm not an expert on the applications. Anyway, I'm hoping to learn a bit tomorrow. And finally, one more example, which also I will not explain properly, but if any of you are familiar with some of the algebraic geometry, which I don't think many of you are, but I'll talk about it anyway. Suppose you fix some topological space X, and then you consider the category of sheaves on X, and with which the morphisms are the sheaf morphisms. Okay, considering I have defined what a functor is, I can say what a sheaf is. So a sheaf is simply, you can look at the open X Open X is basically the category of all open subsets of X. Morphisms are just inclusions. So you have your open X, and then you map it into the and you take a functor from the category, from this category into the category of abelian groups. Then F, this is a contravariant functor. So like you dualize this, but it's okay. Let's not worry about that. A contravariant functor is simply a functor such that instead of giving you a map for a map from A to B, instead of giving you a map from FA to FA, it gives you a map from FB to FA. And a nice example is the dual for a vector space. I'm not sure if you have seen dual. Right, it's mostly second and third. So if you have seen dual. But yeah, dual reverses the arrows essentially. So that is a contravariant functor. Anyway, so upon pre-sheaf just means contravariant functor from open X to the category of abelian groups, then you will say that this is a pre-sheaf of abelian groups on X. A sheaf is a pre-sheaf satisfying two additional axioms, which I will not bother describing. I'm already well past the time limit, but basically it allows you to glue functions in some, and that is very vague, but that is the idea essentially. You glue functions in a consistent manner. So then you have your sheaves on X. My claim is that you can put an abelian category structure on F. Okay, I have not even defined what an abelian category structure is. An abelian category is basically something which lets us mimic whatever we have done for modules and chain complexes, where for each morphism we have kernel, co-kernel, you have finite direct sums, you can talk about exact sequences. That is the point of an abelian category. The point is that there is an abelian category structure on sheaf X, sheaves on X, and then if I take a short exact sequence of sheaves, 0, there is something called a global sections functor. So what is the global sections? X itself is an open subset of X. So there is a map Fx. So Fx is some abelian group. So basically I am mapping each sheaf to its corresponding abelian group Fx, and it turns out that this is left exact. Let me just right. This is left exact. So F prime X, Fx, F double prime X. So we can construct its right derived functors. The point of saying all this is that when you have a topological space and a sheaf on the topological space taking values in some abelian category, there is another way to construct cohomology. Or did I even mention cohomology? But these right derived functors are known as sheaf cohomology. But yeah, when you have a topological space and a sheaf of say abelian groups on the topological space, then there is another way to construct cohomology with coefficients in abelian groups, and that is known as check cohomology. And like it is a big result in algebraic geometry that when your spaces have enough structure, these two are one and the same. Hopefully some of you will go on to learn these things later on and then revisit this in the YouTube video, and then you will be like, Sankha that talked about. But anyway, that is all I have to say for today. Thank you all for attending. Right. References. I will mention one reference. Now, the thing about Weber is that many of the proofs are like the proofs that I have given. He will only give an idea of the proof and then you are left to justify it. So do not, if you are trying to learn the subject, do not rely on Weber by itself. Use the internet. There are lots and lots of good online notes which go into proper proofs of things you might be struggling with. So use the internet to your benefit. Yeah, that's all.
Okay, so does anyone have any questions? Okay, then let's thank the speaker. And tomorrow tomorrow we will have a talk on homological methods by number theory by Amit, so please make sure to attend. Thank you.